Hello again, and welcome to another day of Advent of Code, and with that, of course, Advent of Code in Kotlin. It is day 12, which, as you might know, is also going to be the last day that we're going to be putting on these live streams. So, everyone who's joining today, want to say a special thank you for having tuned in throughout this campaign and for tuning in one last time today. By now, you probably already know the drill. Most importantly, I got my tea and I got my reading hat. But from you folks, I want to know, how did you feel today? How did the puzzle go? Let's share some opinions. Today's combination of tea is very fun. First of all, I've got a unicorn-style teacup, which I've got years and years ago. This is actually a video game reference. If someone can point out from what video game that is, I'll be very impressed. And it's my winter cookie tea again, which, as I just found out, is actually mostly apple. It's about 54% apple, bunch of aroma, lemon juice, but actual cinnamon, which, again, thoroughly impressed me. So, let's have a look here. Hi everyone, hi from Brazil. Thanks so much for these streams. Already miss it. I'll miss it too, but with the vacation coming up, I think it's gonna be for the better, so that you can experience a lot of nice things happening in 2023 as well, because we're obviously not stopping putting out cool little content for you. Let's see here. Cropub says, "Whoa, shortest path day. Let's go." Yeah, it is quite nice. It is actually a very fitting conclusion, because I feel like 5 or 6 guests that we've brought on in their predictions mentioned some kind of path-finding algorithm of something that was going to come up eventually. So it's nice that we still got to see that and that we get to discuss it today. Yeah. Hi, Alexander. Last AOC stream. Yes. The streams were the best things of AOC this year. That means a lot to me. Personally, I can't entirely agree. I think probably the best thing is always the puzzles, because without those, we wouldn't have any of this. But I'm glad that you enjoyed them, and I really do hope that you are gonna enjoy this last one just as much. I'm not seeing a lot of difficulty estimations here, so let's hear some difficulty estimations in here as well. Olaf says, hey, sad day. Yeah, I hope that's only in reference to the fact that streams are ending, and not that, once again, the puzzle was way too easy. By now, we of course know Olaf from yesterday and from his daily complaints. I'm just joking around. Well, accept your apology if you do all the story narration for the remaining days when you're back in January. All of them, huh? Man, that's 12 days. Actually, it's 13 days, I just realized. Sorry, so in Germany, not sure how that actually is anywhere else. Our advent calendars usually only go to 24, because we celebrate on Christmas Eve. We don't celebrate on Christmas morning. So the 24th is where Christmas happens, and then it's just 2 days of visiting family and like hanging out, complaining that all the stores are closed. You know, the usual. 12.5 days, because the last day only has one puzzle. Yeah, true, but if we started summing things up also by difficulty level, then I think we probably haven't even reached half yet. So it's all a matter of perspective, right? Thiago says, today was pretty hard for me. Never done mazes before. Yeah, well, in that case, let me make my recommendation again. This wonderful book by James Buck, called Mazes for Programmers. I actually looked inside, and the algorithm I use today is not actually covered, as far as I can tell, in this book. I briefly checked, but it has a bunch of others covered, which you could use to also solve this problem. So you can always check that one out. Alexander says, I'm an idiot in graphs and pathfinding, so for me it was crazy hard. Last time writing some pathfinding was about 10 plus years ago. Never had to do it at work. Well, you didn't have to do it at work this time either, did you? But yeah, no worries. Again, Advent of Code is something where you can learn something new. But if you do have interesting resources that you maybe use to solve today's problem, you can, of course, share them in the chat as well. I'm not sure if you can actually post links, but otherwise, maybe some terms of blog posts or books that you referenced might be useful. All right, I think everyone has. Jonathan says I used Dijkstra because I was worried that for part 2 the costs would change. Well, for that context to make, for that comment to make sense, we probably need to put it into context, and for that we need to get into the problem statement. But before we can do that, I of course need to introduce my guest. So today I have the wonderful Dave Leeds with us today, who is maybe best known as the guy who draws cartoons about Kotlin? Question mark?
That's right.
I think so. Yeah. Hey Dave, how are you?
Yeah, doing great, Sebastian. How are you doing?
I am excellent. I'm just enjoying this cozy evening, as I always have. It's kind of fun, because usually before you do like a webinar or like some kind of presentation, I'm always like a little nervous, you know. I can feel the nerves. But with Advent of Code and with like the nice little background music we have going on, and just with the fact that everything's laid out, I don't know, it's just kind of relaxing. I'm actually not feeling stressed during these things.
Yeah, music goes a long way to kind of soothe the nerves, you know.
I think that's right.
Plus, yesterday we also learned some good mathematics to try to keep your worry level down, right, with the modulus arithmetic.
That's right. If when in doubt, and if that doesn't work, just divide it by 3 if you can. So these are definitely the approaches that I think they should teach in like yoga class or something if you want to be deeply relaxed. So you're you draw comics or cartoons. Sorry, actually, what's the difference? I keep forgetting.
Oh, I normally think of comics as being, either like a comic strip, which we don't see too often these days, or a comic book. But yeah, I refer to them as cartoons, but then cartoons a lot of times people think are animated as well. So cartoons, comics, take your pick.
I see. And your goal there is just kind of to teach people Kotlin?
Yeah, I've really enjoyed a number of books where I felt like the material was presented in a way that was very accessible. And I think a lot of times illustrations, cartoons and things like that can make something that might otherwise be a little harder to grasp feel more accessible and easier to get into.
I guess that's also a good way to kind of have a hook in your memory that you can kind of come back to if the drawings somehow portray something maybe unusual or put things in a funnier context than just the abstract concepts.
Yeah, that's true.
Back. So how's your experience with Advent of Code? Is this the first time that you're actually doing Advent of Code, or do you have a history?
Yeah, this is the first year that I actually committed to doing Advent of Code. I had heard other years from some of my friends about how they enjoyed it. But a lot of times I'd heard about like the leaderboards and kind of the competition elements of it. And my wife and I are not very competitive people at all. And so I think for a few years, I kind of decided not to do Advent of Code just because I kind of felt like there was too much of the competition element that I didn't want to have to engage. But this year I kind of discovered that Advent of Code can really be like whatever you want it to be. It's really you take the puzzle, and some people try to solve for solve it in the fewest lines possible. Some people try to solve it with the most performant code possible. And so you can really, you don't have to try to get it done fastest. You can just try to learn something. And I think what I've seen is that a lot of people have learned things from other people, just looking at other solutions, discovering standard library functions that they didn't know existed, that kind of thing. And so, I'd say for anybody watching the stream, if you've got friends who maybe haven't decided to take the plunge on Advent of Code, and maybe they're just not the competitive type, let them know. Get the word out that they can really use it to flex whatever exercises that they want to engage in.
Which, of course, is also a great segue for me to once again shout out the fact that not only do we have leaderboards for those competitive folks, you also have the chance to win some Kotlin, or specifically Advent of Kotlin, swag just by participating, just by doing about 3 of the puzzles, or at least attempting 3 of the puzzles, tagging your repository with the AOC 2022 in Kotlin topic, and just making that open source. And that's all you need to do. You don't need to solve them all at once. You don't need to solve them within any allotted time limit. We'll just draw a couple of lucky winners. For all the details on that and how you can set topics and so on, make sure you take a look at the link in the description. And while your cursor is down there, maybe leave a like actually as well. I'm not sure how much people interact with these streams usually, or whether they just have them sitting there on the side. So we always appreciate that. And if you've made it this far, if you've made it to day 12 and you have not yet subscribed to the channel, then I mean you can do that as well at some point. So I have to actually say that I'm always surprised about how much I can still learn from Advent of Code. It's like even from the first couple of days, seeing other people solve problems in different approaches or with different like little neat tricks, I think is one of the most exciting things. Do you have a favorite about something that you've learned this year?
I will say I have been pretty surprised at some of the solutions that people have pulled off with a pretty small number of lines of code. I've been aiming a little bit more for getting full types involved so that I can really model the problem domain. But there are some people whose their minds just go straight to the algorithm itself, and so I've been really impressed with some of the solutions on just how little code it can take to pull off a solution. Where I think I spend a little more time on like modeling everything and analysis on it. But I've been pretty well impressed with some of these people, and they get it done so fast too.
Oh yeah. I think if you haven't seen that one yet, make sure you check out the episode or the stream we did with Roman Yelizarov, who kind of shows, I guess, code which embodies what you just described quite nicely. It's very fast code, it's very efficient code, but he also was very blunt about the fact that he said, well, he was just gonna do the thing that was the fastest for him to type out, admitting it is hard to write non-performant code, which I guess that's a very on-brand statement, if you ask me.
Yes, it is.
Yeah, but I'm always delighted about the solution as you described them, where there's a bunch of like where you go deeper into the type system and you write something that looks closer to maintainable code. Just because I think you can take away more things from that, even if you're not faced with specific algorithmic problems, but just in general Kotlin code, you kind of can get an idea of how you would maybe structure or like separate your code in like different pieces.
Yeah, good opportunities to make use of type aliases, to make use of value classes and things like that. Just kind of wrap those types and have types that model that problem, and then you can come back to it. And I'm hopeful that most of the ways that I'm solving these problems this year, if I look at it 6 months from now, that I would at least be able to understand what problem it was trying to solve.
Okay. Yeah, I think that's honestly, for some of my code, that would already be a tall order. I'll be very honest with you. I've been looking back into some of my previous years, and then there's a bunch of zip and windowed functions without any like names. It's just like val foo equals input.zip.window.chunked, and then like three lambdas stacked inside of each other. Which again, for Advent of Code, I'm perfectly okay writing. If anyone else ever had to read that code again, or I had to actually explain it well, it will probably not be my choice. All right. So we've talked very abstractly, so I am curious about what your code is going to look like. And for that, of course, we first need to introduce the problem of day 12. So the hat
thing
goes on. Yeah, we'll stick for the last day as well.
Yep.
And we'll continue with our dramatic reading of day 12. Hill climbing algorithm. You try contacting the elves using your handheld device, but the river you're following must be too low to get a decent signal. You ask the device for a height map of the surrounding area, your puzzle input. The height map shows the local area from above broken into a grid. The elevation of each square of the grid is given by a single lowercase letter, where A is the lowest elevation, B the next lowest, and so on to the highest elevation, Z. Z? Yeah. Also included on the height map are marks for your current position, capital S, and the location that should get the best signal, capital E. Your current position, capital S, has elevation A, and the location that should get the best signal, capital E, has elevation Z. You'd like to reach capital E, but to save energy, you should do it in as few steps as possible. During each step, you can move exactly one square up, down, left, or right. To avoid needing to get out your climbing gear, the elevation of the destination square can be at most one higher than the elevation of your current square. That is, if your current elevation is M, you could step to elevation N, but not to elevation O. This also means that the elevation of the destination square can be much lower than the elevation of your current square. For example, we have a small map here. Here you start in the top left corner. Your goal is near the middle. You can start by moving down or right, but eventually you'll need to head towards the E, lowercase e, at the bottom. From there, you can spiral around to the goal. Here we see which kind of paths are kind of allowed, and then we kind of end up doing this spiral motion until we end up at the capital E. In the above diagram, the symbols indicate whether the path exits each square moving up, down, left, or right. The location that should get the best signal is still E, and dot marks unvisited squares. This path reaches the goal in 31 steps, the fewest possible. What is the fewest steps required to move from your current position to the location that should get the best signal? Gonna quickly open up the puzzle input here so that you can kind of get an idea of how big of a map we are working with. And Dave, where did your mind go when you read this description?
Yeah, so it's been a while since I've done any kind of path traversal algorithms. And so the very first thing I did was reach for a book off of my shelf. I don't have the mazes. Was it called Mazes for Programmers? Is that what you had?
That's right. Mazes for Programmers.
Okay, yeah, I don't have that one. I've got this old one that's a programming game AI by example. I remember had a few different path traversal algorithms in there. And it's also written for C++, which makes it a little bit of a challenge to translate to Kotlin. But I at least kind of knew where I needed to head. That we were going to have some kind of a graph and some kind of a in order to get the shortest path, we were going to need a breadth first search algorithm.
Okay, nice. Was there a particular reason why your mind went to breadth first? I think we've had a couple of people here also say say Dijkstra, which I guess is the I think the classical shortest path algorithm.
Yeah, I'm not actually sure the difference between that. Is Dijkstra a kind of breadth first, or is it implemented completely differently?
Dijkstra is an all pairs shortest path algorithm.
Okay.
But I think it operates on a similar principle. You also have your queue and explore from there.
Okay. Yeah, similar to A star, I think is another one. But it's been a while and I don't know the nuances between them.
Yeah. So I remember that A star usually introduces some kind of heuristic to, I think, make it even more performant. But I will admit that I have never implemented an A star algorithm on my own. Maybe, I don't know, maybe that's something nice to look at over Christmas break, since I would be curious. There's an article from Red Blob Games which provides an introduction to this algorithm and a bunch of other ones as well, by the way, including visualizations, sample code, and also, interactive visualizations of the different algorithms. So maybe that's interesting as well. I just haven't really gone through this one yet because I figured I don't want to just type it out. I want to understand at least a little bit of what's happening. Need to invest that time. Okay, so breadth first search. Then let's see what that looks like in your code, shall we? Just gonna open this one up right here, and I guess we're gonna start off in your main function.
Yeah, great. So I've found most of the days of advent of code, I've ended up kind of working on three different pieces. One is the part to parse the input. Another one is the models that those things get, that input gets parsed into. And then third is the script part. And a lot of times the script part is just, by the time you model out the domain pretty fully, it's pretty straightforward from there.
Yeah.
So here you can see I've been putting parse functions on the companion object for the model that it's getting parsed into. So
let me jump to your cursor there.
Yeah. Let's see here. Let me switch over to here. Okay. Let's go to here where we're parsing this. Actually, let's take a look at the terrain real quick.
Yes.
Terrain here is just a simple, really it's kind of a grid of these plots. And so with each of the characters representing a height for that particular plot of land, I just made a terrain class that's going to represent the entire map, as it were.
Okay, and a plot is what?
A plot is a single cell in that grid.
Okay, understood.
So a small plot of land that you would step to, for example.
Okay, but this is an enum, or this is just a type alias for the integer that's underlying it, or what are we looking at there?
Yeah, I actually put in a little bit more data so it'd be easier to work with later. So just a little bit up here, we've got the plot data class where we've got its x and y locations, which you could try to derive from the terrain, by looking at where the indexes are. But I decided to go ahead and put it in there anyway. The height is just converted to an integer. And then I've got the plot type, and if we go up, we can see we've just got the start point, the end point, and I couldn't come up with a better name than other for everything in between.
Fair enough. Okay.
So the terrain represents this grid of plots, and really we just have this this one function. This is where the shortest distance function is where we're doing. This is where the breadth first algorithm happens. And you mentioned already, Sebastian, that this is working on a queue, and that's exactly what I ended up doing here. Okay.
So in your case here, you chose a linked list. Okay. Now that's an interesting pick. Yeah, that I think that one needs a little explanation, maybe.
Oh, yeah, sure. I was just looking for what queue. So queue itself is not a class, so you can't instantiate. It's just an interface. And so I just poked down the Java docs to see what implementations there were. And I really just need a first in, first out queue. And I was surprised to see linked list was in there, but I guess they add a few extra functions to it to make it implement queue. So it did the trick, and it's a linked list, and we're all familiar with linked lists, so it was kind of easy to do.
Very true. I think the other couple of days we saw people who wanted to use something like a queue use an array deck. So now I'm kind of curious actually if array deck implements the queue interface as well.
It looks like it does, yeah.
Look at that. Very cool. Well, look at that. I honestly I didn't even realize that array deck implemented any of those interfaces, because I think queue, that one comes from the JVM, right?
That's right. Yeah.
Yeah. Okay.
Is array deck also that's also from the JVM, or is that
no? Array deck is actually a Kotlin library function.
Great.
At least. Well, this is a Java file, which now I'm a little surprised. I guess this depends on whichever import you have. Since this one is a Java util star, so maybe can I get this to resolve to the Kotlin version instead?
Let's see.
I'm trying to figure out what. Okay, so if I'm just gonna have to get rid of this one very briefly.
You can remove the import if you want.
And okay, then we don't even know the queue anymore, but it knows the array deck. Okay. So if we just import this one, all right, that one does not import queue. Understood. Okay, fair enough. It has a very similar API regardless, but we're just gonna keep it as is then. And yeah, I mean, you can still take the array deck from the JVM. That still works, and it avoids the linked list, which I think most people say you generally don't want to have, but for this case, I think it would have been fine either way.
Anyway, you might be right. I haven't checked performance implications of these choices. So.
Neither have I. Always remember, the only performance data that's actually relevant is the one that you benchmark, like the one we've seen the previous days. All right, sorry, we're getting hung up. Go right ahead then. Okay,
let's see. So we'll just keep walking down the implementation here. So there's a little bit of a spoiler here in that. The second part kind of shifted the approach here, where originally I was starting at the start point, working my way to the end point. So I won't give away too many surprises here yet, but for reasons that will become obvious later, working from the end point to the start point is going to be helpful for the next part of the challenge. So that's why the initial here is going to be the endpoint. So what we're going to do is we're going to keep track of all of the plots that we've already visited, so that as we're stepping around from one to the other, we don't backtrack onto the same one, or we don't step forward onto the same one that we've already been on, or else we'll end up going in circles probably. So we're keeping track of that with a set. And then the queue is part of the way that normally I've seen the breadth first search algorithms working. And so we're going to start by putting by stepping onto that endpoint plot. So when I say step here, I'm kind of thinking in terms of like you're starting in one spot and you're stepping onto another plot, and then you step onto another plot, that kind of thing. Mm-hmm. And so we start by just saying, let's put this in this queue. We're going to put this starting point that we're in. We're going to go all the way through all of the steps, and it'll be a little clearer as we get farther down why this is just a while loop. So we're just going to keep working on it until we run out of things to process, in other words. On line 44, we'll get our first step by pulling it out of the queue. So we just pull it. And we're going to check to see if the step that we're in, if that plot that we're on is the destination that we're looking for. And if it is, we'll return whatever the distance is. So what you don't see here, which is probably relevant for me to tell you, is when we added the step on line 41, there's a second, I'm going to go up to the definition of step here. The distance starts with a 0. So we will, as we step towards something, we'll increase that distance. But we're starting at 0 because that's exactly where our start point is.
Okay.
And so we check to see if this matches the destination, and we can see down on part 1, we've got our check is just saying, is the plot type the start? Because that's we're working our way from the end to the start. So if it is that start point, then we know we've arrived and we can return our distance to it.
Mm-hmm.
I've got a log statement here, which can be turned on or off with a little Boolean that we've got down at the bottom. But this is just for me to be able to keep track of things when I was debugging to make sure that the search algorithm was working like I wanted.
Yeah.
And then all of the interesting stuff happens here from line 49. So we're going to take the plot that we're on, and we've got 4 spots potentially that we can move to. And so we're going to get the adjacent coordinates from that plot. So I'm going to go up to the plot class again here. And you can see we've got this adjacent coordinates. Coordinates, by the way, is just a type alias up here for a pair of int and int. I get a little confused when everything's nested like that inside those diamonds. So I did a type alias there. But you can see all we've got here is just a list of the 4 directions that you could go. So if this current plot is on X and Y, then we could step 1 to the west, I guess, which would be X minus 1, but staying on Y. And you can see the second one's going to be stepping to the right, and then north and south as well. Yep. So that just gives us all of the coordinates. Now, that doesn't tell us whether those coordinates are actually within the bounds of the terrain. So let's come back down here. So that's what we're doing next here on line 50. We take those 4 coordinates, and we're going to map them down here and get plot. And this is just checking to see if that next plot of land, so we got these 4 directions, if they're within the bounds of the terrain, then we'll return the actual plot object for it. If it's not, then it'll just be a null, and we're going to map not null here.
Okay. So this is just kind of to kick him out.
Say that again, Sebastian.
This is essentially just to kind of kick out the elements that would be out of bounds.
Yes, the things that are like so far north that there's nowhere to step from there.
Yeah. Okay.
All right, and let's see. So after that, we've got our check to make sure that we've got the rule about how much higher or lower the step can be from where we currently are, and so we're also going to boot the ones that are not applicable. Does that make sense? So based on the height.
Nice. I do find it. It does take a little bit of a twist in my brain because the original description said we were kind of walking up, right?
Yes.
And you've inverted this here. We're gonna see why, I guess, in a second. But that's just something that I need to be very focused on as I stare at this code.
That kind of knocked me for a loop as well when I was trying to figure that piece out there.
Mm-hmm. Okay. And then after that, you what do you get from all of this? You return at...
We have a list of potential plots that we could step onto.
Okay.
And so at this point, we know it's not going to be out of bounds. We know it's not going to be one that's disqualified on account of its height. So we know whatever's in this list at this point is going to be a potential direction we could go. Yes. The one last thing we need to check is to make sure that we haven't already been there. And so we talked about that already for a moment. And that's where we're keeping track of the visited plots here with the set.
Okay, so this is the filter in line 52. Make sure we don't go in circles.
That's right. And then after that, we add this step in that direction for the to the queue, and then of course we make sure that we add that it's been visited, so that we don't end up there again. Now this step toward is just a little bit of a convenience function to make it kind of read well, right? Step toward it kind of sounds nice. Mm-hmm. And the idea there is like stepping toward that plot. And so back up here on step, you can see we just create another step. We take the plot, we're going to step onto that plot, and we're just going to add one to the distance of where we already are.
Ah, okay. I see. So you're keeping track, the essential part for finding the shortest path here is that you keep track of your path length inside the step.
That's right.
Okay. And then once done with all of this, you just return it, I guess, and that's
So we'll just keep looping here over the steps. And so what we've done is the main thing that all of this work has done is we're adding the next possible steps that we could take to this queue. And so we've already, when we did the poll here, we've already knocked off that first item off the queue, and we're putting more steps on the queue each time. So if you have just one direction you can go, which is the situation at the beginning of the puzzle, or the beginning of the test data, then you're basically you're pulling one step off and you're putting another step on, and it kind of makes your decision pretty easy. You're going to step onto that next thing, and just kind of doing one at a time for a while. But eventually you get to a spot where you've got more than one possibility of where you can step. And that's where things get a little more interesting. So what we do is we'll take possibly two things and put them, two step options, and put them onto that queue. And now you've got two of them. And as you're knocking them off, you're going to handle one at a time. But the reason it's called breadth first is you're actually slowly working your way out on all of these guys. And so that's kind of how this queuing approach works, is that you're putting the next things to process are going to be those next steps. And then when you take off that first, say you've got two options on the queue, you take off that first one, maybe that one reaches into, another step or two that you could do. That goes on the end. And so the next thing to get processed is going to be the second option from that current spot, if that makes sense.
Yeah.
So you just kind of keep plugging away at it until you get to the end, and hopefully you don't end up on line 59 where you've got no way to get there.
Yeah. In my case, I definitely managed to, in one of the configurations, I managed to do that one, and I was like, whenever in Advent of Code there's a pathfinding problem and I managed to hit like an illegal state exception, I'm like, okay, this just went from 1 hour to 5 hours.
Yes.
Yeah. So really glad to see that I hopefully in your solution that didn't bite you too hard here.
Not too hard, but yeah, there was a little bit when I was sweating it here. So
yeah. Okay, and then from there, once you've found the shortest path, that's pretty much all there is for the first answer, right?
Yeah, once you eventually, in this while loop, you'll eventually come across whatever it is your destination is, and we'll return that distance for it.
Nice. And I guess if we go back down to your main function, that's exactly... No, that's... I'm still seeing this... Okay, so this shortest distance lambda at this point you just used. Let's just briefly go back to that one.
Yes.
Just to check here. Again, that was your is destination part, which just determines whether you found, I guess, your goal.
Mm-hmm.
But apart from that, pretty much you just invoke the function and that's it. Okay.
Yep. Yeah, just check it to see if that's the one.
Nice, very elegant. I can already see that part 2 is not gonna be a very long discussion or well, a very long change.
You should have seen where I started from. So,
so we're just gonna quickly go back and we're gonna take a look at part 2 to see what's going on there. How Dave was able to make a minuscule change in his code to support that case as well. So hat goes on. My headphones are giving me a little bit of trouble today, but that's okay. Part 2. As you walk up the hill, You suspect that the elves will want to turn this into a hiking trail. I'll also zoom this in a little bit for you folks. The beginning isn't very scenic though. Perhaps you can find a better starting point. To maximize exercise while hiking, the trail should start as low as possible, elevation A. The goal is still the square marked capital E. However, the trail should still be direct, taking the fewest steps to reach its goal. So, you'll need to find the shortest path from any square at elevation A to the square marked capital E. Again, consider the example from above. Now, there are 6 choices for starting position. 5 marked A plus the square marked capital S that counts as being at elevation A. If you start at the bottom left square, you can reach the goal most quickly. Specifically, this path reaches the goal in only 29 steps, the fewest possible. Actually, we can kind of try to follow this one here. So it goes over, up, down, over, up, and then kind of in a spiral up until we end up at the end. What is the fewest steps required to move starting from any square with elevation A to the location that should get the best signal? All right, Dave.
Yeah, so
I imagine that with this kind of approach that you have here, you're kind of grinning now.
Well, I'm grinning because this is not how I started. So I started doing from the start to the end, and so I definitely reworked the solution to get the second part. Make it easily solved for both the first and the second.
Did you do it like Roman first, where as you were solving it, you were just overwriting your first part of the solution, or did you just kind of knead the code until it was capable to handle both parts at once?
Yeah, I figured I'd try just kind of making changes here and there to try to get it to handle both. The big the big unlock is the idea of needing to start from the end, even though they're saying, walking from the start to the end. Starting from the end and working your way backwards is actually the same number of steps either direction, right?
Yep.
But you can solve both problems that way. And so it's kind of like once you solve for the second solution, you're like, oh, well, okay, we can just change the first solution to do the same thing, just searching for that starting point instead.
Yeah, I think this is actually a really clever approach, and one that I'll be very blunt. I didn't even figure that one out this morning because I was still too sleepy. So the idea is just, well, if you want to get the shortest path from like A to Z is the same as the shortest path from like Z to A. Like they're the same length, and since you're only interested in the length, you might as well just invert the whole approach and just go down and stop the moment you encounter your first your first potential start point, which I guess saves you the trouble of testing all the potential candidates here.
Yeah, that's a good point. You could do it the other way, where you just say, loop over all of the ones that start with A, right, and work your way to the end. That's certainly another option as well.
Yeah, which is a great segue for us to talk a little bit about my code. Again, yeah, if you have a hunch about how I solved part 2, make sure you put that one in the chat. I think you're gonna have a bit of an idea soon. We're gonna start as usual in our main function, where I'm just reading the input as lines, and I've created something called a topographic map. We've seen this kind of pattern before, where you just have a capital letter function to create an object for essentially in lieu of a constructor. So I just made one of those, And my code is still very messy because this is very close to what I just wrote in the morning. I needed to create a topographic map. I needed to keep track of, at least for part 1, the start and the end, as well as all the heights. Now, I will admit that once again, maps of vector2 to integer is not a very efficient way of storing this. But it allows me to very quickly like iterate on things, like index things, and especially if you're in situations where all of a sudden you're working with a very sparse matrix, like if you just need to keep track of, for example, a few objects flying into space, you might have an easier time keeping track of just a bunch of vector 2s. So that's why why this is usually my first approach. Of course, what Dave did with a 2-dimensional list is a much more efficient approach. Yeah, but since I just need to fill in this pattern, right? So I need to keep track of my start and end functions, which I can grab out when I eventually iterate over the capital S and the capital E letters. And apart from that, we're doing the classic thing where we're just adding to our map that we're building at the given position the height. And again, this seems to be a little bit of a recurring trick. Of course, we say that one is whatever our character is minus a, so that it all gets normalized down to like a 0-based index. So a would be 0, and then all the other following letters would be 1 incremented. Because I couldn't even be bothered to do this math in my head in the morning, I think that should be 26, but maybe it's 25, because... No, I think it should be 26. I was just like, all right, well, we know that the end is supposed to be on elevation Z, so I can just manually do the Z minus A, and that's going to work just fine. Yeah, and then at the end of the day, we return all of this as a topographic map object, simply to hide away the fact that we're working with mutable stuff here, and we have a bunch of mutable variables. This one I kind of got influenced a little bit by our discussion with Olaf yesterday about hiding away mutability in a scope and then exposing only the immutable bits afterwards. So you'll see, again, in the topographic map, this is no longer a mutable map. You can't actually change the contents. It's just read-only, and the same thing for start and end. So these are now immutable data structures. Okay, and from there, I needed to have a function that would find the shortest path. And specifically, I gave this one the parameters for the start and end position, at least in this case, because I also wanted to reuse it for the second part, and the height map. We can just pass that one in. And then if you take a close look at the Wikipedia article for breadth first search, you can see that one gets auto-completed for me and that it's very much purple. If you scroll down a little bit, I think you'll find a couple of... unfortunately, this is not gonna... maybe it'll work. You can definitely see that the algorithm is pretty much a one-to-one translation of what was happening on Wikipedia. So, because that's about the amount of capabilities I have when I'm sleepy-brained. Yeah, I used an array deck, but it's the same as the queue that Dave used from a conceptual perspective. I had an explored or visited set. I made sure that I add the start position to the explored set as well as to the queue, and then we do kind of the same iteration down here. I just have a couple of helper functions that we're going to talk about in a moment. All of this is pretty much the same as beforehand. Once we reach our end position, we can generate the path length. We're going to talk about that in a second. The one big difference that I have in comparison to Dave is that I keep track of the kind of parent relationship. So which node precedes the next node in my list, using just a simple mutable map for vector2, which just allows you to say, I am standing at this node where would I have been coming from? And you can just look that one up in the map, which we'll use to kind of trace the path once it's done. Yeah. Just like Dave, I had an extension property called adjacent, which in my case just creates more vector 2s, in this case of the left, right, up, and down variety, which are pretty much exactly the same as Dave has defined them. Yeah, of course, you also want to make sure that these are actually in your map, and you want to make sure that the step is somewhere between the minimum value of an integer and 1, which is of course just a very crazy way of just saying less than or equal to 1. But this is the one part where I kind of got tripped up by reading a little bit diagonally this morning. I absolutely missed the fact that I could step down multiple steps. So originally this was like, it's between 0 and 1. Because surely you wouldn't go down, right? But no, as it turns out, you can get down as far as you want. You just can't get up anymore. And yeah, from there, this is once again the classic approach of just adding things to your explored list, to your parents, to make sure that the kind of the predecessor relationship is stored correctly, and then you add, of course, that specific connection, if it has not yet been explored, to the queue. I have to say, this one feels much more like the one that's on Wikipedia, but yours feels much more like the one that should have been written in Kotlin. It makes a nice use of the list comprehensions. I am kind of limited to a filter here and then go straight back to a loop. So good job on that one, Dave. So then, of course, the only question remains is, with this whole like list determined, I of course still needed to figure out how long the path is, because all I knew was I can somehow compute all the parent relationships, but that doesn't mean I know how far I've actually walked yet. So I need to go through and I need to count this. And what you do is you walk backwards through your parent relationships. You start with the vector, and you just keep track. And then what you do repeatedly is you take one step to your predecessor and you increment the length. And you do that over and over and over again until you've reached the start position, because again, you're walking backwards, and then you return the length of that path. Just because I kind of already figured the solutions are gonna look quite similar between the two of us, I wanted to provide one more different implementation for finding this path. And I wanted to specifically do one that makes use of the tailrack modifier. So for those of you who don't know, tailrack, if you mark a function like this, then first of all, two things are true. First of all, your function has to be tail recursive. That means that the last call in a function may either return a value, or it may do a recursive call and nothing else. You can't like add a value after this, or you can't like merge two lists in this function. It has to be just a plain call to the function itself. When you do that, due to computer science magic, that means that the compiler can actually unroll your or convert your recursive function into one that uses a loop, which obviously performs much better and also doesn't have the problems like getting stack overflows because your path is too long and you're recursively calling into a function over and over again. These tail calls are being kind of eliminated in this case. You're just getting the raw version here. Yeah, so what does this recursive function look like? Well, as usual with recursion, we start with the base case, which is just if we've reached our start position, then we will return the accumulator. So that's something that has been given into us from whatever call. That's just where we kind of keep track of how far we've gone. If we haven't reached that function, if we haven't reached that place yet, that means we need to take a look at our parent. So recursively, we say, okay, well, how far is it to get to our parent? That's kind of what we're doing here. And since we need to also keep track of the one step we did, the accumulator gets added 1. Now, remember that this is something that I couldn't do, like, I need to give this accumulator into the function. I don't have any way of keeping track of this outside. I couldn't have another return afterwards. Like, I couldn't compute it and then return it afterwards. I have to do it in here. So at the end of the day, the function that knows how far we've gone is going to be the very last invocation. And that's going to return step by step all the way through all the previous invocations, the actual value. Yeah. We'll see. We'll briefly check out a couple of comments here. Jonathan said, I just iterated over every A. Huh, interesting. We'll see we'll see what Sebi did in just a second. For hiding mutability, I used the build map function. Also very elegant. That also works. Very cool. And the trick to get it tailrack is to do the stack as an additional parameter. That's pretty much what happens here. And since we are not interested in actually any intermediate values, our stack or anything that we want to keep track of across the individual function invocations, we just store in this integer. We're just interested in the length. Now, classically, you also want to be able to call this function with some kind of initial value. In Kotlin, you can, of course, just specify this one by saying equals 0. I have to admit, and this is only personal preference, I don't quite like this because I very easily forget while writing the function that I have a default parameter for this. So if I had this one in here, I could write this code and be like, okay, it compiles, I'm done, which of course doesn't do what I want. So this is one of the rare cases in Kotlin where I actually make use of overloading. And I have a second function which has the same signature, except it doesn't take the accumulator and just calls path length 2 using the accumulator of 0 just to initialize it. That one behaves functionally and in terms of its result exactly as the regular path length 2 function that we saw up here, which is a loop. And I would venture a guess that most likely even the compiled bytecode or a decompiled bytecode would look quite similar between the two because they're both just using a loop. Yeah, I just make sure that these are actually the same and I'm not talking any crazy stuff, so I check that one and throw an exception if for some reason these deviate, but they don't, which is nice. And they didn't on first try, I'm being honest here. So yeah, after that we can just return that, which solves our part 1. That's done with that. And then, of course, if you are Dave, then you do something clever like walk the whole thing backwards. But if you are Sleepy Sebi in the morning, that means that you just find all the values that have a height of 0 and consider them as a starting point for your find shortest path function, and you just take the minimum of whichever path has been the shortest. And I can just quickly demonstrate this one just so that you realize that at least for the input statement here, this isn't even that crazily long. So you'll see that this one takes it takes a couple of seconds, but it's not go grab a coffee and wait for your algorithm to terminate type slow, which definitely was my worry for a bit, but it seems to be fine. Yeah. All right. Thoughts on this one, Dave?
Yeah, I like it. I like that you found an opportunity to work the tail recursion I've been looking for an opportunity on Advent of Code to be able to do that, but I'm not greatly well versed in more of that functional recursive style, so I haven't gotten daring enough to use it yet.
Yeah, that's fair. I every time I use it, I get a little bit of flashbacks from my OCaml classes in university, which was a very, very fun class. But as usual in languages where you're working with a pure functional subset, it gets a little bit mind bendy with all this base case specifying and trying to figure out how much state you have to pass through in every recursive call. Gets quite funky. But yeah.
Otherwise, looking at it, and the kind of core part of that while loop is really very similar between the two of ours.
Yeah, definitely. I am curious how close would you say was your implementation to the one that you found in your book? Was that pretty much just a verbatim copy, or did you have to make a lot of changes?
It's mainly, it just gave me the structure, which is not too different than what you got off of Wikipedia. I suppose I could have just pulled up Wikipedia instead and gotten the same thing. I just mainly needed to remember how the basics of the algorithm work. Yeah.
No, but I like that the intuition is going for a book instead of just the regular old Wikipedia article. Which also, by the way, reminds me that Maya a while ago asked what is the link for the A* blog post again, which, by the way, is Red Blob Games. I can put that one also in the chat. There we go. Jonathan says, mine was more like 1 minute, but still faster than rewriting. Yeah. I always get a little bit very nervous and twitchy when my Advent of Code algorithm doesn't terminate within 5 seconds. I'm like, it's gonna be one of those where it's gonna take 6 hours or 30 days to terminate if I don't find a better algorithm.
But... yeah, using big integer for yesterday's problem, right? Just keep still going.
Exactly, just keep banging on that one. I do remember that Matt Parker, I think, talked about at some point about finding a very long anagram or something like this, and he said he wrote some very bad code and he let it run for 30 days. So if you don't know Matt Parker, he's a stand-up mathematician who also signed this watch.
Yes. By the way, I gotta say, Sebastian, that was the trailer that you had done for Advent of Code, where you had the watch. That was the selling point for me. That's my favorite watch, and I've got the exact same one.
That's really lovely to hear. For me, it has, of course, special value because it's the same watch that also appears in Back to the Future, which if you look in any of my shelves, you'll probably find a Back to the Future trinket somewhere. But it's also just an excellent watch. I'm wearing that one right now. So yeah. Yeah. But of course, by the way, I encourage all of you not just to check out the Red Blob Games introduction to the A* algorithm, but of course the stuff that you make as well, Dave. So
thank you. Yeah.
I think the classic one is typealias.com, which I'm gonna link right now if you want to talk just a little bit about what you have on here, what people can expect.
Yeah, sure. So I've been doing illustrated guides to Kotlin for a little over 5 years now, and especially for people who are just starting off. For the past few years, it was a project that I thought I'd wrap up quickly, but it's been a few years now. But I've been working on building cumulative topics, and so I've kind of called it an online book. But different chapters that kind of just walk you through from the very foundations of just if you're brand new to Kotlin or even programming, really, you could get in on kind of the ground level and build up those topics one by one. I've got a few things in there about the generic variants in Kotlin. I've got a few things in there about sequences that people like. So yeah, most of them have cartoons in them.
That's really cool. Did you teach yourself the cartoon drawing to do this, or did you do that before? Like, what's the history there?
Yeah, cartooning's been kind of a hobby of mine for most of my life. I never really took any art classes or anything. The handful that I didn't do too well in, actually. So it's just kind of been a hobby of mine. And when I started working on the website, actually my wife said before I started working on this website, she was like, you should include your comics in there. And I was like, I don't know, people might not take me seriously if I do that. But a few months in, I noticed that that's actually what people connected with the most. So that's kind of how I ended up just including a lot of cartoons and illustrations that way.
Nice. And you also have a YouTube channel, right?
Yeah, just started that off a couple months ago, so I've only got a handful of things there. But yeah, working on getting more content up on videos as well. That's been well received, so thank you everybody who's said very kind words on that. So still building that out, but we'll add more stuff here soon. Very
cool. So if you want to hear and see more from Dave, make sure you check out @typealias on YouTube as well now. Yeah, this I haven't quite gotten used to the fact that there's @handles on YouTube now.
Yeah, it's pretty recent.
Yeah, but yeah, make sure you take a look at that. And I think with this, it's almost time for us to say goodbye. But of course, we are not leaving without one more visualization. So graciously gifted to us by Olaf. Again, if you haven't seen him on the show, make sure you watch the recording of yesterday's stream. And I have to say, it was a really nice gift of Eric to us, I guess, that we would end up with the last day of getting a really nicely visualizable problem. So this is how this is what the map actually looks like, which I have to say is quite crazy. I didn't realize looking at the map that there was such a clear path upwards. I really thought there was going to be more hills to circumnavigate, but that's kind of what it looks like visually. So we're gonna run that one again at half speed since it goes pretty quickly. But yeah, it really does seem that there's just one main mountain, and we can see the difference between how breadth first search and A* with its heuristic approaches solving this maze, quote unquote, which is what this essentially is. You're trying to find the path that gets you to the destination the fastest.
It's fantastic. I love it.
Yeah. And yeah, you can definitely see the difference of first just kind of doing like flooding all of the path elements versus trying some heuristic which gets you an approximation of a solution, I guess, a whole bunch quicker. If you do want to learn more about what A* works like, don't ask me. Check out the blog post we linked beforehand. All right. Yeah, just to be clear here, we also got Anirudh saying people don't take you seriously. People XKCD would like to have a word with you. We appreciate your non-seriousness, which is great.
Great, yes.
Yeah. Yeah. And I think with this, I'm gonna let this play out one last time. I want to say thank you so much, first of all, to you, Dave, for coming on today.
Yeah, delighted to be here.
Yeah, and to everyone who tuned in at any of the days that we streamed. I had a lot of fun. This campaign was semi-impromptu organized. I'm super glad that we managed to find so many interesting people from the Kotlin community who contributed in their own way, whether it was providing us with just a simple solution that they would like to have shown on screen, whether it was visualizations like this one, and of course with all the people who actually came on stream as guests. So yeah, if you want to see if you've missed any of them, make sure you go take a look once again at the stream recordings. And of course, since this is my last opportunity, I will once again remind you that there is Advent of Code swag to be won. Make sure you find all the descriptions in make sure you find all the links in the descriptions, and make sure you maybe join a leaderboard, tag your repository correctly so that you are set up for getting some wonderful Advent presents. I would maybe Christmas presents, but they're probably going to be... Someone still has to merge all the leaderboards and stuff, so it's going to be a while. Don't expect them by like the 25th. But they'll be around eventually. So yeah, check that part out. Thanks for doing the weekends and also for the extra stream step. Have a wonderful rest. Thank you so much. And I hope that, of course, all of you will still enjoy the rest of Advent of Code and have wonderful holidays and a happy new year as well. So thanks again for being a part of this. It was really, really great. Okay. Take care, everybody. Bye-bye.